All right, the third and final way to classify a chemical reaction, we talked about precipitation reactions, acid-base reactions, and then we're going to get to this next and last one. But I always like to introduce this one with these pictures. Okay, so you see lots of pictures here, and I'll always ask this question: what do all of these things have in common? So usually, I'll ask questions like, to the class, I'll ask, what pictures do you see here? What are in these pictures? And people might say different things, but I'll just kind of walk you through these. This first one in the top left-hand corner is a pacemaker. My grandfather almost had to get one of these, but he's actually in his 80s, and so doing surgery was a little bit more risky than they want to do, so they just put him on some heart medication. But it's a pacemaker, keeps your heart in rhythm. People will get this if they're a little bit younger and they're having heart issues. But anyways, that's a pacemaker. And then the top right hand picture is it's a cochlear implant. I'm actually not sure how to spell cochlear, and I probably would spell it wrong. But it is for people who are deaf, and they can get these implanted. It's a life-altering device for sure, but it takes these auditory signals, and it has a transmitter that actually helps them understand and hear speech and language. So it's a very helpful tool. And then the bottom one is obviously looks like somebody in the military. And oftentimes, people who have done that kind of service, especially overseas, or experienced trauma serving in the military, can have syndromes like PTSD. And so this would be a huge decision, but they can get these implants to help regulate emotions and things like that. And so that's what you see in the bottom picture. But I always ask, what do these things have in common? And the answer is they all run on small batteries. Whoops. So then I usually ask people to consider how important batteries are. Life as we know it, I don't think would function without batteries. Our cell phones run on batteries. Obviously, our computers and vehicles run on batteries. And, we could think of more examples probably, but they're pretty important, needless to say. And so the reason I bring up batteries and use that as a way to introduce redox reactions is because batteries run on redox reactions, okay? If redox reactions did not exist, then batteries would not exist. Okay, so this is how a battery works: is redox reactions, and you sometimes can have rechargeable batteries that can keep them running continuously. But the redox is just the root word, and you can expand that really. You'll hear me say oxidation, reduction reactions. That's really the full name of our third classification here, third type of chemical reaction. Oxidation reduction reactions, or the shorter version is redox reactions, okay? All right, so what is a redox reaction? It is one in which electrons are transferred from one atom to another. And you guys should be very familiar with this idea of transferring electrons. Now, we have been talking about this since we introduced valence electrons and understanding what ions are and how ions are created. Cations are created when electrons are lost or given away, right? And anions are created when electrons are gained. Okay, so you guys are familiar with this idea of transferring electrons. And I also want to differentiate this from our second kind of reaction that we talked about in the previous video, which were acid-base reactions. Acid-base was the kind of reaction when a hydrogen atom is transferred from the acid to the base. And so here, we're just getting a little bit more particular. We're not talking about atoms being transferred, but just electrons in and of themselves. So I will specify these bottom two blanks, and then we'll look at this figure. So oxidation is the loss of one or more electrons, meaning the atom or element is giving away one or more electrons, okay? And then reduction is the gain of one or more electrons, okay? Now I want to think what happens to your charge if you give away electrons. Here, if you give away electrons, charge increases, right? You might go from being neutral, 0, to being like a +1 or a +2, which is, again, how you get cations. What happens if you gain electrons, okay? On the other hand, if you gain electrons, your charge is reduced. It goes down. You might go from being a 0, neutral, to a -1 or a -2, like an anion, right? So I want you to think of this: when you're gaining electrons, your charge is being reduced, and that might help you remember what the process of reduction is and how to differentiate that between the process of oxidation. Another way to differentiate it is with this acronym OILRIG, which stands for, I'm going to abbreviate, oxidation is loss, obviously, of electrons, and reduction is gain. Obviously, again, we're talking about of electrons, okay? So oxidation, O-I-L, oil, R-I-G, OILRIG. Okay, oxidation is loss, reduction is gain. And this figure is just showing you these processes, and it helps to kind of get your mind out of the box of just like transferring one electron, or you know, a loss of electron always taking you from 0 to +1. We're used to, with a cation, forming a cation, you know, you're starting at 0 and you're becoming a +1, or you're starting at 0 and you're becoming a -1. Well, this figure here, which is in your textbook, kind of expands your mind, because that's not the only way oxidation can happen. You don't always start at 0, okay? So, for example, look at this first top row in the figure. If we have something that is a -2 and it gives away an electron, it would become a -1. This is oxidation. If we had something that started out as a -1 and it gives away an electron and it becomes neutral, it becomes 0 charged, that's also oxidation. And then these two are what you'd be most familiar with, something becoming a +1 or going from a +1 to a +2. That is all oxidation. If you follow this figure to the right, all of these processes, as you read it from left to right, are oxidation. Okay? On the flip side, if we take any one of these right here and follow this figure to the left, the process that we see is reduction. So now we're just reading these arrows to the left. If we have something, well, we'll just look at the top one. If we have something that is a -1 and it gains an electron, okay, so reduction is gaining an electron. So we take an electron plus something that is a -1, we combine them. Now we have an anion here that is a -2. It has gained an electron. That's reduction, okay? So this might not be a very comfortable thing for you. You got to kind of, I would maybe pause this or rewatch it and just walk through this first slide again, because understanding these steps right here are going to really make oxidation reduction a lot easier for you to get, okay? But we're going to look at two practical examples, two real reactions, and put oxidation reduction kind of into play and see how it works out in a reaction. So we have this reaction right here. We have copper. It's a solid. It's reacting with silver nitrate. Ag is silver, NO3 is nitrate. It's aqueous. And when they react, what happens? Could you tell me what kind of reaction this is? And I don't mean tell me if it's precipitation, acid, base, or redox. Obviously, it's redox here. I'm using it as an example of redox. But could you tell me, is it combination, decomposition, is it single, double displacement, or combustion? Could you tell me what kind of reaction it is from that standpoint? And if you look at this closely, we have an element, and then we have a compound. Okay, go look at your notes if you're not sure and see which one that matches. When you have an element and a compound, you'll notice that copper is essentially taking the place of silver, combining with nitrate. So maybe you have it now, but this is single displacement. Okay, single displacement. And I bring this up because single displacement reactions are always redox reactions. Okay, you can count on that. Single displacement reactions are always redox reactions. Now, they're not the only kind of redox reactions, okay? I'll give you another hint that combination reactions are also redox, okay? And again, I'll explain more about why that is in a little bit, but those are going to be some helpful tips and identifiers, especially on the exam if you remember these things, for identifying or classifying reactions, okay? So what is happening? We have copper, and essentially it's just trading places with silver, okay? Copper is joining up with nitrate, and then we have silver by itself right here on the product side. All right, so what happens to copper and what happens to silver? Well, let's think about from an electron standpoint, because remember here, redox is all about trading electrons. So let's go through and try to assign charges to all of these things. And copper is by itself, and so it's not a cation or an anion right now. It's just an element. And elements don't have any charge, so we're just going to put a 0 on copper, all right? Now, could we assign charges to silver and nitrate here? Y'all should know that nitrate is always -1 because that's a polyatomic that you have memorized, and silver is a +1, okay? Now, on the product side, things are going to be a little bit different. On the product side, silver is the one that's just a plain old element, and so as an element, things have no charge. So we're going to give silver a 0 when we're thinking about what charge it would have. And now copper is in a compound, and so it's the cation here, and it's combined with 2 nitrates. Okay, you see that? This little subscript 2 nitrates. Nitrate is still just -1. Nitrate does not change. But copper here is no longer 0. It was 0 on the reactant side, but now it's a +2 cation. So this brings up a good point if you're confused about why this is. Elements have 0 charge. Ions have charge. Positive, I guess I should say, have positive or negative charge. Okay? Elements, no charge. Ions are what carry charges, right? So that's what happens to copper, and that's what happens to silver. But now let's just summarize this. Overall, as you go from reactant to product side, how are things changing? That's what you want to ask yourself with a redox reaction. So let's read for copper here. In red, it says we start out with 0 charge and we become a +2 charge. So copper, the way I like to abbreviate it is I'll write the element and then I'll say it goes from 0 to +2. Okay. Now, think about, is this oxidation or is it reduction? Did copper gain electrons? Does that make sense? Did it gain electrons or did it lose electrons? Well, if you gain electrons, your charge should go down. So it didn't gain electrons. It lost electrons, right? It gave up 2 electrons. So this is oxidation. So we would say copper was oxidized. And then silver in the blue here, I'll change my color to blue, starts out as a +1 on the reactant side. Now notice this whole thing down here, this whole thing is not including nitrate, okay? Nothing's changing with nitrate, so it kind of pulled nitrate out just so that we can see specifically what's happening with copper and silver. So don't be confused about like, well, where'd nitrate go? But silver is a +1, that's what we said, it's a +1 on the reactant side, and then we said it becomes 0 on the product side, which is also what is mentioned right here. So to go from, if we just summarize, +1 to 0, our charge is decreasing, or it's reducing, right? So we gained, that doesn't happen unless you gain electrons. We gained electrons, and this is reduction. Okay, it was reduced. Here's a picture of this. If you put a copper wire into a solution with silver nitrate, this is silver nitrate solution, look what happens. It grows silver on it. It kind of looks weird. And then the solution becomes kind of green because the solution gets copper in it. Anyways, kind of cool. So let's fill in these blanks down below. Your head might be swimming right now, and let's try to summarize what is happening in this redox reaction. So redox reactions always, redox reactions involving ionic compounds are usually straightforward. Look at the change in charge. And for now, I'm using this word charge. I'm going to put it in quotes. We're going to use the word oxidation numbers in a little bit. But you're going to think of it, it's going to be very similar to understanding like ionic charges, okay? To determine which compound is reduced and which is oxidized, right? And that's what we did, copper and silver. Let's look at another example. I'm going to walk through this one a little more quickly. This is video, so you can pause it and rewatch if you need to. Here we've got potassium iodide and bromine. This is also single displacement reaction. And so let's go through and assign the charges, right? So because we have an ionic compound here, potassium iodide, potassium is the cation, iodide is the anion. Bromine is by itself just an element, so it has a charge of 0. Let's go to the product side now. Iodine is by itself. Okay, so bromine is going to displace iodine. Remember we said nonmetals displace anions, which is exactly what you're seeing here. So on the product side, iodine has a charge of 0. Potassium doesn't change. It's a +1 on both sides. And bromine here is a -1. So what happens to potassium? What happens to iodine? That is summarized down below. If you look at the red, iodine starts out as a -1 charge, okay, as the anion. This 2 here is just for balancing purposes. That does not apply to the charge. Okay, each individual iodide anion is a -1 charge. And then on the product side, it becomes 0 charge. So iodine goes from -1 to 0. Is this an increase or a decrease? And that should be a simple answer for you. This is an increase, okay? So to increase in charge, do you gain electrons or lose electrons? Remember, if you're gaining electrons, you're being reduced. And here we're increasing. And so iodine is losing, we could say lost electrons. Anytime you lose electrons, this is oxidation. So iodine is being oxidized. All right, bromine, in the blue here, we go from 0 charge to -1. So Br 0 to -1. All right, is this an increase or a decrease? 0 to -1 is a decrease, and you can only decrease if you gain electrons. Now, don't be confused by this word gain. Gain doesn't mean you're increasing. And that's what a lot of people can think. You're gaining electrons, which have a negative charge. So because you're gaining electrons, you're being reduced in your charge. All right, so down below it says an iodide ion gives an electron to bromine, forming iodine and bromide ions. So an iodide ion is oxidized as its charge increases from -1 to 0. Bromine is reduced as its charge decreases from 0 to -1. Okay? And this is all because electrons are being transferred from iodide to bromine. All right, now, what if your reaction doesn't contain ionic compounds, okay? Up here, these first 2 reactions we've looked at, this was an ionic compound. One previously, all these contain ionic compounds. What if it doesn't contain ionic compounds? Well, then we can't necessarily think of what we're assigning to these atoms as charges, okay? All of these ionic charges that we're writing in up here each time, well, these are easy to do because we have ionic compounds, but we don't assign charges to covalently bonded molecules. So this is where the idea of oxidation numbers comes in. I highly encourage you to read pages 151 and 152. It's not a lot of reading. This walks you step by step through oxidation numbers with several good examples. But what is an oxidation number? They're simply, they are numbers that help, what's the word I want to use? They're numbers that indicate if elements or atoms are electron rich, electron poor, or neutral. Okay? Now, I want to tell you, they are going to many times perfectly match ionic charges. Okay? So, most of the time they will match ionic charges. I think I can even say that. But they do not always necessarily match ionic charges, okay? So I'm giving you this disclaimer that oxidation numbers do not necessarily imply ionic charges, but many times they will be the same as if you were assigning ionic charges to elements, all right? But they can be different, and I'm going to give you an example in just a minute down here with HNO3 of how they can be different. But let's walk through these rules. Okay, a few rules on oxidation numbers. These rules will not be listed on the exam for you, but they'll be very helpful for you to know. So rule number 1 says an atom in its elemental state has an oxidation number of 0. You guys remember? Let me go back up. Like right here, when we were putting the 0 on the bromine or the 0 on the iodine, anything that's just an element by itself has an oxidation number or a, quote, charge of 0. Okay. Next rule is a monatomic ion. Mono, but remember we dropped the O and just write monatomic, means an ion that's like by itself. Okay, a monatomic ion, one atom ion, and so it's not a polyatomic ion. A monatomic ion will have an oxidation number equal to its charge. So again, this is just reiterating what I've said, that oftentimes oxidation numbers will perfectly match ionic charges. Now in a compound, or I should also say in a molecule, like a covalently bonded molecule, an atom usually has the same oxidation number it would have if it were a monatomic ion. Now in a covalently bonded molecule, like CH4 for example, this one's actually really tricky. I should have probably thought of a different one. But we would assign, yeah, that's actually not a great example to start you guys off with. What is a good example? Probably like H2O, water. Okay, water is a covalently bonded molecule, but we would go through and assign numbers as if these were charges on an ionic compound. And then they, so that would be like hydrogen. You would think of hydrogen having a +1 and oxygen having a -2. Okay, which is what they would be if they were ions. And then lastly, it says number 4, the sum of oxidation numbers in a neutral compound is 0. That sounds very obvious, right? But we know that when we write ionic compounds, they should be neutral overall. And so that means all the oxidation numbers have to add up to 0 the way all the ionic charges add up to 0. Now, let me show you an example with HNO3 where the oxidation number does not match what the ionic charge would be. I'm going to just briefly draw this out. I'm not going to give you the perfectly correct Lewis structure. I'm just going to draw these. I know we should have lone pairs, and I know oxygen doesn't get one bond. I'm not focused on Lewis structures right now. I am just showing you, honestly, you could draw these in. Fine, I'll do it. It's actually bugging me. All right, now what looks weird here? You know what looks weird? I'll tell you what looks weird. Nitrogen looks weird. I don't want to do it in pink, though. Can you see yellow if I do yellow? Nitrogen looks weird. Look at that. Nitrogen has 5 bonds. What the heck? This is what HNO3 nitric acid would look like. All right, and if we were to go through and assign oxidation numbers, I would want to ask you, what charge does oxygen usually have if it's an anion? Okay, and hopefully you're shouting at me, -2. All right, so let's go through and write a -2 beside every oxygen. We've got 3 of them. And if we were to put a -2, oxygen is one of those atoms that will pretty much always, it's always predictable. Like it'll always be a -2. It doesn't do anything weird. And I like oxygen for that reason. Hydrogen here, actually let me get to hydrogen in a second. But what do you know about nitrate overall? Nitrate, just NO3. This is a polyatomic ion. What charge does nitrate have on it? And because you all have your polyatomic ions memorized, you know it's a -1. Now, for nitrate to add up to a -1 overall, that is going to be the sum of all your oxygens plus whatever nitrogen is. And so far, we have a whopping total of -6 in our charges on oxygen. -2, -2, and -2. Okay? So for this to be a -1 overall, you know what that means? This is where it gets weird. Nitrogen is a +5 here. Its oxidation number is a +5. And that's weird because we know nitrogen has 5 valence, and we know that it usually always wants to gain 3 more and be a -3. But this is why I told you, disclaimer, that oxidation numbers don't always imply and don't always match ionic charges. And here, for things to make sense and add up, nitrogen is a +5, oxygen is a -2, and we have 3 of them. And total, that gives us -1. And then hydrogen over here to balance it all out to 0 because HNO3 is a neutral compound. Neutral compound is a +1. Hydrogen is, right? So nitrogen is a good example here of how oxidation numbers don't match ionic charges all the time. Now, am I going to ask you to walk through and do something like this on the exam? No, but I wanted to show you an example because there may be times you are assigning oxidation numbers that don't match the charges you would normally think. That's a pretty good thing for an atom or an element. But it wouldn't be like something quite like this. It'd be a little more simpler. Okay, let's do some practice. This video is already getting pretty long, so I have several more slides, and I am just going to do this top practice just for time's sake, and then we'll see how quickly we can wrap this video up. So, which element is being oxidized and which is being reduced in the following reactions? Tip, first assign oxidation numbers. All right, so we're going to heavily rely on these 4 rules, assign oxidation numbers, and then see if we can identify what's oxidized, which is the thing that is losing, loss of electrons, and then whatever is being reduced is gain of electrons, okay, gaining electrons. All right, so silicon, Si. You know what I notice? It's by itself, so it should get an oxidation number of 0. Know what else I noticed? Chlorine is by itself, so it should get an oxidation number of 0. What kind of reaction is this? This is combination. And remember earlier I said single displacement and combination reactions are always redox, okay? And then on the product side, we have SiCl4, silicon tetrachloride. So, because this is a neutral compound, the oxidation number on silicon plus 4 times the oxidation number on chlorine, because we got 4 of them, well, okay, so that's why I'm saying 4 times, because we have 4 chlorides, is going to have to add up to 0. So let's see if we can fill in these blanks. Well, let's go up and read our rules, okay? In a compound, I'm looking at rule number 3. An atom usually has the same oxidation number it would have if it were a monatomic ion. So silicon, this is main group 4, and we said when we were talking about like valence electrons and ions that main group 4, like carbon, silicon, they don't usually form ions. So we have no idea what kind of charge would typically be on silicon. But we do know for chlorine that this is main group 7. This is a halogen. And halogens always form anions with a little -1 charge on them. All right, so I would bet a lot of money that if chloride, if we assigned an oxidation number to chloride here, it would have to be a -1. And it is, okay? So I'm going to plug this -1 in right over here in our equation because that is going to be our number on chloride. All right, now I bet we could determine what the oxidation number on silicon is. So 4 times -1, that is obviously going to be -4, plus what is going to add up to 0. And the answer here is a positive 4. So that means the oxidation number on silicon is a positive 4. Okay? Now, if you have no idea how I just got positive 4 on silicon, I would encourage you to pause this video and rewatch everything I just said slowly. Okay? As many times as you need to for that to sink in. And if you still don't get it, please email me. Please come visit me. Please stop me after class or in lab sometime, because I usually have students ask questions on this, like, how did you get the +4? And so that's why I tried to walk you through all of this right here. But this takes practice. It's usually not very comfortable the first time you hear it. Anyways, now let's see, can we identify what was oxidized and what was reduced? So silicon is changing and chloride is changing. Sometimes you will have elements that are not changing at all. And you don't want to focus on those in the end. You just want to look at the ones that are changing. So silicon goes from 0 on the reactant side. So these are the numbers that I'm looking at, 0 to a positive 4. All right. Now, chloride goes from 0 to a negative 1. So I'll rewrite chloride in blue. It goes from 0 to negative 1. All right. Now you need to ask yourself, I like to focus on which one's being reduced first, like which one has a charge that is reducing, and you know that's reduction. And that is going to be chloride here. This is reduction. Chloride's being reduced. Okay, it is gaining electrons to go from 0 to a negative 1. That's reduction, which means by default, silicon is oxidized. You will always have both, something being reduced and something being oxidized. In fact, you can't have one without the other. If electrons are being given away, they have to be picked up by somebody. Okay, so these always flow in tandem. You'll never have one without the other. Okay, I hope that's helpful. I'm going to skip over this next one for time's sake. There's actually a lot of practice problems here. I will for sure do these problems as a review before exam 2. But this is already a long enough video, and I really just want to get to my concluding remarks. So, oxidation reduction always occur together. That was one thing I actually just said. Bullet point number 2, when one substance loses an electron, meaning it's being oxidized, another substance must gain that electron. It's going to be reduced. Now, these last two bullet points usually throw students for a total loop. They are kind of funny to think about, and again, this is sometimes just the nature of chemistry, but let's read them. The substance that is oxidized, I'm gonna highlight that. The substance that is oxidized and gives up an electron causes reduction. Okay? So the substance that is oxidized is causing your other thing, your other atom or your other element to be reduced. So you know what we call it? We call it the reducing agent. It is the agent of reduction. It is causing something else to be reduced. Itself is oxidized, but it's causing reduction, so we call it the reducing agent. The substance that is reduced gains an electron, causes oxidation, so we call it the oxidizing agent. So just think of them as being flipped. Whatever is reduced is the oxidizing agent. Whatever is oxidized is the reducing agent. Again, I know, it's kind of crazy. And then here's just some summary review, okay? The reducing agent, it's the one that is oxidized. It causes reduction. If you're being oxidized, you're giving up electrons, you're losing electrons, and you're becoming more positive, or quote, your charge or oxidation number is becoming more positive, sorry. Don't worry about this last one. That's something if you're going into another chemistry class I would go into, but don't worry about that last one. Okay, and then a few things on oxidizing agents, a few characteristics there. You can read over those. Here's my last slide I want to get to. How does this relate to you? I talked about batteries earlier, but I wanted to give you a very direct, like, health science example, okay? We would not live or breathe if we did not, if redox reactions didn't exist. And this is how respiration, this is how metabolism works. So breathing and extracting energy from food all run on redox reactions. Our bodies depend on redox reactions. It's really very amazing. And so here I have glucose and reacting with oxygen, making CO2 and water, and energy. And this is amazing because in all actuality, when you look at the whole compilation of reactions that cause this overall net total exchange between glucose and oxygen, 24 electrons are transferred from carbon atoms to oxygen atoms in the metabolism of glucose. And magically, our bodies extract energy from the process to make ATP. So, all very cool stuff. These questions are for a review that we'll do before exam 2. All right, I hope this was helpful. Please send me any questions you have, and I will continue on with chapter